Today we're going to go over Chapter 3, Lesson 4, Proofs with Perpendicular Lines. So, the distance from a point to a line is... the distance from a point to a line is the length of the perpendicular segment from the midpoint to the line. It is the shortest distance between the point and the line. So, for this one, they want us to find the distance from point A to line B. D. Now keep in mind, I'm going to highlight those points. Point A is right here, and line BD is right here. Now, there's three paths point A can take to that line. Now, the shortest is AC, which I will highlight in green. This line right here. That would be what I would consider you guys to do the distance formula and to solve it. Also, because it has a 90-degree angle right here, we know that's a perpendicular angle, which is the shortest distance from that point. So I will write the distance formula up here so you guys can see it.
So which one? -3 is it minus? Is it minus? Wait, what are the order? And then plus y2 minus y1 squared.
Now I'm just writing down what I said so you guys have it in your notes. Alright guys, I'm going to write the points. If you had a chance to work it out, that's awesome. While I was writing, if not, I will write it in as well. So points A are -3, 3, and points C are 1, -1. I'm going to choose the C to be the 2s, so x2, y2, and I'm going to choose the x to be x1, x1 and y1. Now let's plug it in. The distance for AC equals this -3 minus 1 squared plus 3 minus -1 squared. This is going to give us AC is equal to -4 squared plus 4 squared, which is going to be, I'm going to write up here, square root of 16 plus 16, which is going to give us the square root of 32, which, guys, that simplifies to 4 root 2. The way, just a reminder, you can use the factor tree to simplify the radicals. We have a 32. Remember, you need two of the sames in order to be able to do it. So I can take a 2 out. So if I take a 2 out, it's going to be 2 and 16, 2 and 8, 2 and 4, and 2 and 2. Now, because we're able to take out, I always like doing it with prime numbers. If you do it a different way, that is fine. I always like to take out pairs of prime numbers. Then I realize I have two 2s. So I just, because again, it's a square, we need 2 of them. I'm going to grab those 2 together. So it's going to be 2 times 2, and that's where this 4 comes from. Now, if you do it a different way, that is fine too. So we have the perpendicular bisector, a perpendicular bisector of a line segment PQ. So that is this one right here, guys. Is the line N with the following 2 properties. N is perpendicular to PQ. Again, it's a lowercase letter, so that's how you call a line. And right here, it's perpendicular to segment PQ, which it's already highlighted in green. And the other property is that N passes through the midpoint of midpoint M of PQ. Since it passes through the midpoint, I want to remind you guys that means that this segment and this segment of the segment PN are equal to each other. Proving theorems about perpendicular lines. So we have a linear pair perpendicular theorem. This is if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if angle 1 and angle 2 are congruent, then G and line G is perpendicular to line H. Now what does this mean? They give you guys a line. Right here is just highlighted. This line, they give you a line. And they say that there's another line cutting it right in the middle. Well, or not necessarily even in the middle. I'm just doing it in the middle. And they tell you that one of the angles is congruent to the other. And because the line is always 180 degrees, if you split that angle down the middle, it will always give you 90. So if that is the case, if angle 1 in this right here and angle 2 are congruent, and that is a straight line, that intersect, that line that cuts the other line, in this case G is cutting H, that means it is a 90 degree, therefore it's a perpendicular line. So perpendicular transversal theorem. So in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So if H is parallel to K, and J is perpendicular to H, then J is perpendicular to K. Now, you guys remember in the last section, we had a theorem about perpendicular lines. Like if one line was parallel lines. If one line was parallel to the other, then it is also so let's call it L, M, and H. You guys remember that if L was parallel to M, and M was parallel to N, then N is parallel to L. So if one is parallel to the other and the second to the third, then the third is also parallel to the first. This is the same thing, but with perpendicular lines. So if with these two, in this case, H and K, which is what they gave us as the example, are parallel, and we have one singular line cutting through one, then it will be also perpendicular to the other. The key part is the two lines must be parallel, and they have to tell you that one of the angles is perpendicular. In this case, it told you that H and K were parallel, and J and H were perpendicular. So you were able to get that J and K, so the bottom one right here, was also perpendicular, because they gave you the order of things. This is, guys, if you guys remember, this would be kind of like your transitive property. It moves through one to the other, if you want to associate it that way. So, proving theorems about perpendicular lines. So, lines perpendicular to a transversal theorem. So, in a line, if two lines are perpendicular to the same line, then they are parallel to each other. What does that mean? So in this example, M is perpendicular to P, and N is perpendicular to P, then M is parallel to N. I want you guys to look at that picture and notice how these two are perpendicular, and M and N are perpendicular to line P. Now, if they're both perpendicular to that one line, they're never going to touch, which is going to make them forever parallel. If you guys can think of it in the sense of this room, you can look at any wall. Let's say the front wall of the classroom is touching the floor, and the floor is the other line. We have the back of the wall. The back wall of the classroom is also perpendicular to the floor. But the two walls across from each other are never going to touch because they're just perpendicular to the floor. So the photo shows that the layout of the neighborhood. So we gotta determine which lines, if any, must be parallel in the diagram and explain our reasoning. Now I want you guys to notice that line P and line Q, which I'm gonna highlight, which are these two, line P and line Q, are both perpendicular to line S. Line S is right here. How do we know they're perpendicular? There's a 90-degree angle right here in both of, let me use a pencil, right here. There's a 90-degree symbol in both of them. So, by the lines perpendicular to a transversal theorem, which we just learned, we can say that lines P and Q are perpendicular to each other. Also, lines S and T, which I'm going to highlight in a different color. Line S is this one and line T is this one. Are both perpendicular to Q, which is this one right here. Now, how do we know they're perpendicular? Again, they show us right here and right here a 90-degree angle symbol. You have to zoom in to see it, but it is there. So by the lines perpendicular transversal theorem, we can also state that S is parallel to T.